Yeah, so this is a question from GATE 2020. The question is, for the components in the sequential circuit shown below, TPD is the propagation delay, T setup is the setup time, and T hold is the hold time. The maximum clock frequency rounded off to the nearest integer at which the given circuit can operate reliably is dash megahertz. So the question is to find what is the maximum frequency that we can apply, clock frequency that we can apply so that it works properly, right? So what is the given terms are TPD, T setup and T hold of flip-flop 1 and flip-flop 2. And if you see here, we have two flip-flops and the output of flip-flop 1 is given to flip-flop 2 through a combinational circuit. Okay, and so it is given here, and the output of flip-flop 2 is directly connected to flip-flop 1. So if I draw the circuit here, I have a flip-flop 1, I have a flip-flop 2, okay, and in between I have a combinational circuit. Okay, so output of flip-flop 1 is connected to input of flip-flop 2, and output of flip-flop 2 is directly connected to input of flip-flop 1, right? Yeah, now we'll see what's the maximum time required so that a valid input is received at the, or is converted into valid output of one flip-flop, right? So for example, say I have an input here, okay, we'll call it as a valid input came at the input, and as per the given data, the propagation delay of this flip-flop is 3 nanosecond, which means this output of flip-flop 1 will be a valid output corresponding to this valid input after 3 nanosecond, right? Yeah, and so if I have an input here, it is converted to the valid output within 3 nanosecond, okay, and this is given to a combinational circuit where each is consisting of a XOR gate and a NAND gate. So total time delay of this combinational circuit is like 2 nanosecond, which is propagation delay of XOR gate, and 2 nanosecond, which is the propagation delay of NAND gate. So totally 4 nanosecond, right? So this combinational circuit has a 4 nanosecond delay, which means this valid output will be reflected at the output of this combinational circuit. I will call it as valid output of this combinational circuit after 4 nanosecond, right? And this is given to the input of flip-flop 2. Now if you see here, the flip-flop 2, the setup time of this flip-flop 2 is 4 nanoseconds. So we know if this is the clock frequency or the clock cycle, the input should be there, right? If say this is the input to a flip-flop, the input should be set up, okay, at the input of each flip-flop, like flip-flop 1 or flip-flop 2, by at least before this clock cycle, at least by T setup time, right? That is T setup, okay, setup time. That is the input should be available at the input of the flip-flop at least T setup before the clock, or rising edge of the clock, rising or falling edge of the clock, depending upon the type of flip-flop, right? Which means this valid output should remain at least T setup before the clock edge, which means here the T setup time, for the T setup time it should remain this input. So what is the T setup here? That is 4 nanosecond, okay. So if we have a clock period which is at least the sum of this delay, then a valid input can be converted to a valid output, okay, valid output of the flip-flop 2, right? So what is the time period? T, I will call this as flip-flop 1 to 2, right? So I will call this as time 1 to 2. The total time required, minimum time required is 3 nano plus 4 nano plus 4 nano second, that is equal to 11 nanosecond at least it should be there, so that this valid input will be received at the flip-flop 2, right? So this is from 1 to 2. Now similarly, if I see here, we have one more path, that is path flip-flop 2 to flip-flop 1, right? So here if you see, if there is a valid output or valid input here, okay, valid input at the input of flip-flop 2, this will be reflected at its output as valid output, okay, after 8 nanosecond. That is a propagation delay, so it requires at least 8 nanoseconds so that it gets reflected its output, okay. And this is given, right, and this is given here, at its input, that is this is valid output, valid input to this flip flop, right? And as previous, this should remain at least the T setup of flip flop 1, so that this get reflected at its output of flip flop 1, right? So we require at least this data to remain at least for 5 nanoseconds after it gets settled. So what is the total time in this loop? So this is loop 1 and this is loop 2. So T2 to 1, okay, time required, minimum time required from 2 to 1 is 8 nanosecond, which is this one, propagation delay of flip flop 2 plus the setup time of flip flop 1, that is, what is the setup time? 5 nanosecond, yeah, 5 nanosecond, that is we require at least 3 nanosecond, right? So the clock period should be, so what is the clock period? This is the clock period, TC. So the clock period should be in such a way that it accommodates both 11 nanosecond and 30 nanosecond, right? So what is clock period we require? Minimum clock required time period we require is the maximum delay time which we require, T12 or T21, right? So that is we require minimum of 13 nanosecond, because 13 nanosecond is more than 11 nanosecond, right? So we require minimum 13 nanosecond clock period so that the data is converted properly. So what is the maximum frequency? The frequency of clock that we can apply is 1 by TC minimum, that is 1 by 13 nano, okay? And if we calculate this, 1 by 13 nano is 76.92 megahertz, right? So the answer is 76.92. Yeah, so this another question from GATE 2020. The question is, the state diagram of a sequence detector is shown below. The state S0 is the initial state of the sequence detector. If the output is 1, then so the question is like, for which of these sequence, okay, the output will become at this end, the output will become 1 for this FSM, okay? So we'll first take the given sequence, right? So the simple method is like, we'll take the sequence itself. So sequence is 0 1 0 1 0, okay? So we'll start from S0 and we'll give each input. So initially the first input is 0. So when the state is S0 and input is 0, so what happens? So here if you see in this state machine, above this arrow there is one data, right? 1 bar 0 or 0 bar 0. Here the first data indicates the input and the second data indicates the output. So it is in this format, input bar output, okay? So what we'll do for the given input data, we'll just go through this the states, okay? So first data is 0 and initially it is as 0 at S0. So if input is 0, what is the path from S0? This is the input, right? 0 or 1. So input is 0, so the state changes from S0 to S1, okay? And what is the output? Here it is 0, okay? Now next data is, input is 1 and the state is at S1. So when input is 1, the state transition from S1 to S2, right? And what is the output? 0. Now next data is 0 and we are at state S2, okay? So which is the path? Path is this one, right? Input is 0 while this is 1, right? So this is the path 0 and output is 0. So the state transition happens from 2 to S2 to S3. Now next data is 1 and we are at state S3. So which is the path? The path is this one, right? This path is S3 to S4, right? And data is 1 and output is 0. Now what happens? The last data, that is 0, comes. We are at state S4 and input is 0. So which is the data? A transition happens here, right? This is 0. So transition happens from S4 to S3, okay? And what is the data output? Output is 1, which means at the end of this sequence, right, input sequence, the output is 1. So option A is the correct answer. When this sequence is detected, the output will be 1, okay? At the end of this data, the output will be 1. Now if we similarly, if you go through these data 0 1 0 1 1 0 1 1 0 or 0 1 0 0 1, for all these the output will be, end output will be 0, right? You can check that. So answer is A. So this is a question from GATE 2020. The question is, P, Q and R are the decimal integers corresponding to the 4-bit binary number 1100 corresponding to signed magnitude, 1's complement and 2's complement representations respectively. So P represents the signed magnitude, right? So signed magnitude representation is P and 1's complement is Q and 2's complement is R, right? Respectively, the 6-bit 2's complement representation of p plus q plus r is. So we need to find what is p plus q plus r and find its 2's complement. So given number is 1100. Sign magnitude 1100. Here this last bit corresponds to sign, right? So if I remove the sign, the remaining term is 0100, which corresponds to 4. So what is 1100? 1100 corresponds to minus 4, which is equal to p, right? In sign magnitude. Similarly, so this is sign magnitude. Similarly, next is 1's complement q. So in 1 complement 1100, this will be signed binary of the corresponding number given, right? So here, how to find what is the exact number? We will just take again its 1's complement. Okay, so taking its 1's complement, it will be like 0, 0, 1, 1, right? So this is equal to 3, right? So what is this 1100? This corresponds to minus 3, which is equal to the q, right? Given q, right? So p is minus 4, q is minus 3. Now in 2's complement, I have 1100. So how to find the exact number which corresponds to 1100 in 2's complement? So here what we will do, first we will subtract 1 from it, right? 0, 0, 0, 1. So how we take 2's complement? If I have a digit, I will take its complement plus I will add 1. So this is actually its 2's complement. So to find what is a, what I am going to do, I will subtract 1 and then take its complement, right? So that's what I am doing here. So if I subtract this, so I have to make this 0, carry will be 1, 0. So this is 1, I will take this 2 here, so it is 1, 0, right? So 2 minus 1 is 1, here 1 minus 0 is 1, 0 minus 0, 1 minus 0, 1. So this is like this term minus 1. Now I will take its 1's complement. So if I take its 1's complement, it will be 0, 1, 0, 0. So this is the value. So what is this? This is equal to 4. So this is equal to 4 and this is its 2's complement and the last bit is 1. So it's a signed 1. So what is r here? R is equal to minus 4, right? R corresponds to 2's complement term of 4, that is minus 4. So p is minus 4, q is minus 3, r is minus 4. Okay, so what is p plus q plus r? That equal to minus 4 plus minus 3 plus minus 4, that is minus 11. Okay, the question is to find 6-bit 2's complement of p plus q plus r. Okay, so what we will do, I have the number minus 11, that which corresponds to p plus q plus r. I will find, okay, its 2's complement. Okay, so how to do that? We'll take 11. Okay, first write 11 in its 6-bit representation. So what is 11? So 1, 1, that is 3, 3 plus 8, right? So 1, 0, 1, 1 is 11 and it should be in 6 bits. So 0, 0, 1, 0, 1, 1. That is its 6-bit representation. So I'll take its 1's complement. So 1, 1, 0, 1, 0, 0 and I'll add 1, right? That is 0, 1, right? So if I add 1, what will be 1, 1, 0, 1, 0, 1. So this is the answer. Okay, 1, 1, 0, 1, 0, 1. So this corresponds to minus 11, which corresponds to p plus q plus r. So in the option, the answer is A, 1, 1, 0, 1, 0, 1. Right? Yeah, so this is again a question from GATE 2020. The question is, the figure below shows a multiplexer where S1 and S0 are select lines. I0 to I3 are the input data lines, En is the enable line, and F of PQR is the output. So what is F? F is, right? So here the enable is 0, right? Input to enable is 0, which means the entire mux is enabled. And we have S1 and S0 as a select lines where P is the input to S1 and Q is the input to S0, right? So there are 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. So we can select when P and Q are 0, 0, we can select the input I0, that is this one. And when P and Q are 0, 1, we can select I1. When it is 1, 0, we can select I2. And when 1, 1, we can select I3, right? So which means when P and Q is 0, 0, the output F will be I0. And similarly with I1, I2, I3, right? So how we can write F, the function F I can write as when P and Q are 0, 0, that is when P, Q are P bar, Q bar, right? 0, 0 means P bar, Q bar, 0 1 means P bar Q, 1 0 means P Q bar, and 1 1 means P Q, right? So when input is S1 S0 is P bar Q bar, the output is F is I naught, right? So I naught plus, or when P and Q are 0 1, then output is I1, right? So when P and Q is P bar Q, then output is I1, that is F will be I1. Or when P and Q is 1 0, that is PQ bar, then output is I2. Or the case is when P and Q are 1 1, that is PQ, the output is I3, right? So we'll just substitute what is I0, I1, I2 and I3 are here. So I0 is R, right? So P bar Q bar into R plus P bar Q into I1 is, here it is 0, right? 0 plus PQ bar into I2 is R, and plus PQ I3 is 1, right? So we have P bar Q bar into R plus P bar Q into 0, that is 0, right? Plus PQ bar R plus P into Q, right? Into 1. So I can combine these two, right? So here Q bar R is common, so P bar plus P into Q bar R plus PQ. Okay, P bar plus P is 1, so 1 into Q bar R is Q bar R, so Q bar R plus PQ. So answer is F is equal to PQ plus Q bar R. So answer is option